Ridgid 425 tripod vise is a compact and portable tool designed for various cutting and threading tasks. User reviews highlight both positive and negative experiences with this particular model. On the positive side, many users have found the Ridgid 425 to be an amazing little vise, emphasizing its extremely lightweight and portability. They appreciate the speed and ease with which it can be set up, often describing it as taking only a matter of seconds. Its suitability for specific needs is frequently mentioned, with strong recommendations given based on its performance. Users have expressed their love for this vise, again pointing out its lightweight design and the simple setup and takedown process. They have successfully used it for a variety of projects, ranging from cutting conduit to threading pipe, and have reported consistent, perfect results. The vise is also described as a great tool that holds up well over time. Users have reported owning it for several months and have found it to be sturdy, durable, and perfectly suited for smaller jobs. However, there are also some negative experiences reported by users. Some users have found the vise to be too small for their specific requirements, expressing a desire for a larger capacity. Others have raised concerns about its sturdiness, mentioning that it wobbles when used to cut conduit. Another point of criticism is that the setup and takedown process is not as easy as some users had anticipated. Overall, user feedback suggests that the Ridgid 425 tripod vise is generally well received, particularly by those who need a small, portable vise for light to medium-duty tasks such as cutting, threading, and other similar applications. Its lightweight design and ease of setup are major selling points. However, it may not be the best choice for heavier jobs or for users who require a larger capacity. When evaluating whether the Ridgid 425 is the right tool, consider the specific tasks you intend to perform and the size and weight of the materials you will be working with. If you primarily handle smaller projects and prioritize portability and ease of use, this vise could be a good fit. However, if you frequently work with larger materials or require a more robust and stable platform, you may want to consider a different model with a higher capacity and more substantial construction. The Ridgid 425 tripod vise offers a balance of portability and functionality for specific applications. Positive user experiences focus on its convenience for smaller tasks, while negative feedback highlights limitations related to size and stability. The choice of whether or not to get this device ultimately depends on the individual user's needs and priorities. When working with electrical conduit, it's important to understand conduit fill calculations to ensure compliance with the National Electrical Code, or NEC. These calculations determine the maximum number of conductors that can be installed in a conduit. The NEC specifies fill limits to prevent overheating and to allow for easy wire pulling during installation and future maintenance. Conduit fill is typically expressed as a percentage of the conduit's cross-sectional area. The NEC provides tables that specify the maximum allowable fill for different types of conduit and conductor combinations. The tables take into account factors such as the size of the conduit, the size and type of conductors, and the number of conductors in the conduit. For example, NEC Table 310.15b3 provides adjustment factors for ambient temperature and the number of current carrying conductors in a raceway or cable. These adjustment factors are used to direct the ampacity of conductors to prevent overheating. In general, the NEC allows for a maximum conduit fill of 40% for 3 or more conductors. For a single conductor, the maximum fill is 53%, and for 2 conductors, it is 31%. These fill limits apply to new installations and to existing installations where conductors are being added or replaced. To calculate conduit fill, you need to know the cross-sectional area of the conduit and the cross-sectional area of each conductor. The cross-sectional area of the conduit can be found in NEC Chapter 9, Table 4. The cross-sectional area of the conductors can be found in NEC Chapter 9, Table 5. Once you have the cross-sectional areas, you can calculate the total area occupied by the conductors and divide it by the cross-sectional area of the conduit. The result is the percentage of conduit fill. For example, suppose you have a 1-inch trade size schedule 40 PVC conduit and you want to install 3 number 12 AWGTHHN conductors. From NEC Chapter 9, Table 4, the cross-sectional area of a 1-inch schedule 40 PVC conduit is 0.864 square inches. From NEC Chapter 9, Table 5, the cross-sectional area of a number 12 AWGTHHN conductor is 0.133 square inches. The total area occupied by the 3 conductors is 3 times 0.133, which equals 0.399 square inches. The percentage of conduit fill is 0.399 divided by 0.864, which equals 0.46 or 4.6%. This is well below the 40% limit for 3 or more conductors. It's important to note that the NEC also requires that conductors be derated if there are more than 3 current carrying conductors in a raceway or cable. The derating factors are specified in NEC Table 310.15b3. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity of each conductor must be derated to 80% of its normal value. This derating is necessary to prevent overheating. In addition to conduit fill calculations, it's also important to consider the bending radius of conductors when installing them in conduit. The NEC specifies minimum bending radii for different sizes and types of conductors to prevent damage to the insulation. The bending radius is the radius of the inside curve of the bend. The NEC specifies minimum bending radii to prevent damage to the conductor insulation during installation. For example, NEC Section 344.24 specifies the minimum bending radii for rigid metal conduit, or RMC. The minimum bending radius for RMC depends on the trade size of the conduit. For a 1/2-inch trade size RMC, the minimum bending radius is 4 inches. For a 1-inch trade size RMC, the minimum bending radius is 6 inches. When bending conductors, it's important to use the proper tools and techniques to avoid damaging the insulation. Hand benders and conduit benders are available for bending different sizes and types of conduit. These tools allow you to make accurate and consistent bends without damaging the conduit or the conductors inside. In addition to conduit fill and bending radius, it's also important to consider the support requirements for conduit. The NEC specifies the maximum spacing between supports for different types of conduit to prevent sagging and damage. For example, NEC Section 344.30 specifies the support requirements for RMC. RMC must be supported at least every 10 feet and within 3 feet of each box, cabinet, or fitting. The supports must be designed to securely hold the conduit and prevent it from moving or vibrating. When installing conduit, it's important to use the proper fittings and connectors to ensure a secure and watertight connection. The NEC specifies the types of fittings and connectors that are permitted for use with different types of conduit. For example, NEC Section 344.42 specifies the requirements for couplings and connectors for RMC. Couplings and connectors must be made of materials that are compatible with the conduit and must be designed to withstand the mechanical stresses and environmental conditions to which they will be exposed. Proper grounding and bonding are also essential for electrical safety. The NEC specifies the requirements for grounding and bonding to ensure that all metal parts of the electrical system are at the same potential and that there is a low impedance path for fault current to flow back to the source. Grounding and bonding help to prevent electrical shock and to protect equipment from damage. When working with electrical systems, it's important to always follow safe work practices and to wear appropriate personal protective equipment, or PPE. PPE includes items such as safety glasses, gloves, and hearing protection. It's also important to energize circuits before working on them and to use lockout/tagout procedures to prevent accidental re-energization. Electrical safety is of utmost importance, and understanding and following the NEC guidelines helps to ensure a safe working environment. When it comes to electrical work, understanding voltage drop is crucial for ensuring efficient and safe operation of electrical circuits. Voltage drop refers to the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can lead to various problems, including dimming lights, reduced motor performance, and overheating of conductors. The National Electrical Code, or NEC, provides guidelines for calculating and minimizing voltage drop in electrical circuits. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. Branch circuits are the circuits that supply power to individual loads, such as lighting fixtures and receptacles, while feeders are the circuits that supply power to branch circuits. To calculate voltage drop, you need to know the length of the conductor, the current flowing through the conductor, and the resistance of the conductor. The resistance of the conductor depends on its material, size, and temperature. The NEC provides tables that specify the resistance of different types of conductors at different temperatures. The voltage drop can be calculated using Ohm's law, which states that voltage drop equals current times resistance, or volts equals amps times ohms. For example, suppose you have a 120 volts branch circuit that is 100 feet long and is wired with number 12 AWG copper conductors. The circuit is supplying a load of 10 amps. From NEC Chapter 9, Table 8, the resistance of number 12 AWG copper conductor is 1.98 ohms per 1000 feet at 75 degrees Celsius. The total resistance of the 200 feet of conductor in the circuit is 2 times 100 feet divided by 1000 feet times 1.98 ohms, which equals 0.396 ohms. The voltage drop in the circuit is 10 amps times 0.396 ohms, which equals 3.96 volts. The percentage of voltage drop is 3.96 volts divided by 120 volts, which equals 0.33 or 3.3%. This is slightly above the NEC recommended limit of 3% for branch circuits. To reduce voltage drop, you can increase the size of the conductor, reduce the length of the conductor, or reduce the current flowing through the conductor. Increasing the size of the conductor reduces its resistance, which in turn reduces voltage drop. Reducing the length of the conductor also reduces its resistance and voltage drop. Reducing the current flowing through the conductor can be achieved by using more efficient lighting fixtures or appliances, or by dividing the load among multiple circuits. In the example above, you could reduce the voltage drop by increasing the size of the conductor to number 10 AWG. The resistance of number 10 AWG copper conductor is 1.24 ohms per 1000 feet at 75 degrees Celsius. The total resistance of the 200 feet of conductor in the circuit would be 2 times 100 feet divided by 1000 feet times 1.24 ohms, which equals 0.248 ohms. The voltage drop in the circuit would be 10 amps times 0.248 ohms, which equals 2.48 volts. The percentage of voltage drop would be 2.48 volts divided by 120 volts, which equals 0.21 or 2.1%. This is below the NEC recommended limit of 3% for branch circuits. Another way to reduce voltage drop is to use parallel conductors. Parallel conductors are two or more conductors that are connected together at both ends to form a single circuit. Using parallel conductors reduces the resistance of the circuit and therefore reduces voltage drop. The NEC allows the use of parallel conductors under certain conditions, such as when the ampacity of the circuit exceeds the ampacity of the largest available conductor. When using parallel conductors, it's important to ensure that the conductors are of the same material, size, and length, and that they are properly terminated. It's also important to direct the ampacity of the conductors according to NEC Table 310.15b3 if there are more than 3 current-carrying conductors in a raceway or cable. In addition to calculating voltage drop, it's also important to consider the effects of voltage drop on the performance of electrical equipment. Many electrical devices, such as motors and transformers, are sensitive to voltage variations and may not operate properly if the voltage is too low. For example, motors may overheat and fail if the voltage is too low. Transformers may experience reduced efficiency and increased losses. It's therefore important to ensure that the voltage at the terminals of electrical equipment is within the manufacturer's recommended range. If the voltage is too low, you may need to increase the size of the conductors, reduce the length of the circuit, or install a voltage booster to increase the voltage. Voltage drop calculations are an essential part of electrical design and installation. By understanding the factors that contribute to voltage drop and following the NEC guidelines, you can ensure that electrical circuits operate efficiently and safely. This helps to prevent problems such as dimming lights, reduce motor performance, and overheating of conductors, and helps to extend the life of electrical equipment. When working with electrical systems, it is imperative to prioritize safety and follow all applicable codes and regulations.